Welcome to this video on how you can simplify several 3GPP 5G new radio transmitter tests. Today we'll demonstrate how to verify transmitter characteristics including power, power dynamics, signal quality, and RF emissions. To show us how easy it is, we have our wireless and RF expert with us today, Alex Krauska. Alex?
Here in our lab setup, we have a Tektronix 6 Series B MSO as our acquisition hardware and AWG 70,000 arbitrary waveform generator as our source, which is producing a single NR carrier at 3.5 GHz center frequency with a bandwidth of 100 MHz. It's an uplink signal with 30 kHz SCS, 256 QAM, 11.5 dB OFDM PAPR. The AWG is adjusted for a 250 mV peak-to-peak to 500 mV peak-to-peak, which is about -11 dBm to -17 dBm 5G composite average power. A Keithley source measurement unit is used to power the device under test. And on the 6 Series B MSO, we're running the SignalView VSA software with 5GNR optional plugin, and we've configured it to analyze the signal captured by the scope on channel 1. For our device under test today, we have a GVA 123 Plus from Mini Circuits, a small scale amplifier, but it illustrates the measurement issues typical for user equipment and base station infrastructure applications. We are using a ZDC-10-01203-S Plus coupler, capturing the input signal on channel 1 at -10 dB down. The output signal from the amplifier is captured on channel 5 and is reading -0.8 dBm. The waveform travels out of the AWG to the DUT, where it's amplified by roughly 16 to 17 dB and then acquired by the 6 Series MSOB, where it is digitized and down converted into IQ data before being processed by the SignalView application. The generator and the oscilloscope also share a 10 MHz reference connection through their back panels. First, I'm going to set up the trigger on my scope to look at the OFDM burst of my signal. For triggering the scope, we select the option to trigger on the magnitude versus time, and we're triggering based on a pulse greater than a limit. And we're selecting a negative trigger, so we're looking for the absence of a pulse. And we've specified the height of the pulse to be 10 millivolts RMS, and we've specified a time limit of 900 microseconds. We're also using hold off to not trigger too quickly, which is about half of the typical 5G pulse of 10 milliseconds. Next, we've set the acquisition settings to use the external frequency reference to set the time base accuracy. Now we'll go to SignalView to set the center frequency and the reference level. The scope generates the IQ data that SignalView can process and analyze. All major measurements and displays can be added as needed by the user, with data accessible for playback later, offline, without the need to capture new signals. We've captured multiple IQ acquisitions and are able to perform multiple measurements simultaneously on the same data. The first test we're going to look at is transmitter output power. Then we'll look at power dynamics using power versus time display and the CCDF display. The purpose of the output power test is to verify the accuracy of maximum carrier output power across frequency range, and to measure the output power accuracy relative to the base station's declared value. Here is an example of the actual measurement result looking at the output on channel 5. From the time overview display, we can set the display to act as a window or gate on the time record to tell the software to only analyze or calculate measurements for the portion that is within the analysis window. What we're showing is the total aggregate power across multiple carriers according to the 3GPP standard, which is close to 0 dBm in this case. For power dynamics tests, you can pull up the power versus time display to show us the time domain view of the power. The CCDF display can also be used to show you the statistical distribution of the power amplitude during the pulse. The peak to average measurement is shown on the right. We can make the majority of these measurements using the SignalView VSA software's standard set of displays. but 5G&R option makes it quick and convenient to set up according to the 3GPP specification. The requirements for transmitted signal quality specify how much the transmitted base station or user equipment signal deviates from an ideal modulated signal in the time and frequency domain. The signal quality is assessed for base station and user equipment by measuring EVM, or error vector magnitude, and frequency error. Here is with the constellation diagram display, we're measuring the mean composite EVM of less than 0.6% with a frequency error of just a few hundred millihertz, so we're getting accurate results as expected. Signal View can measure and report all of the signal quality parameters shown here in the summary view across multiple component carriers. Given the number of frequency bands and operational modes, such as carrier aggregation, emissions testing for 5G is significantly more complex compared to prior cellular technologies. There is now a much larger number of harmonic and spurious byproducts that could result from co-site interference, from sub-6 GHz band and millimeter wave 5G transmissions, and given the proximity of antennas to compact devices, the resulting interference products could be substantial. Unwanted emissions testing is intended to limit emissions according to the standard specification, and there are 3 main tests that we'll cover today, including occupied bandwidth for in-band emission tests, and for out-of-band emission tests, we'll use adjacent channel power display, and for other spurious tests, we'll use the spectral emission mask display. Here's an example of an occupied bandwidth measurement for our 100 MHz carrier per the 3GPP standard. The available unwanted emissions tests within the software extend to spectral emission mask, as well as adjacent channel power, as shown here.
Thank you, Alex. 5G&R is among the growing set of signal standards, applications, and modulation types supported by Signal View vector signal analysis software and is supported across Tektronix's line of instruments. In addition to the 6 series, we can also make these measurements on Tektronix spectrum analyzers, the RSA 5000 and RSA 500, as well as high-performance ultra-wideband DPO 70000 oscilloscopes. You can either run the software on the Windows operating system of the oscilloscope or on a separate PC. Remote desktop applications can be used to remotely access the scope operating system. For automated testing, Skippy remote interfaces are available to accelerate the transition from the design process to manufacturing. The Tektronix AWG 70000 provides low noise, flexible generation of multi-channel wideband signals complying with the 5G&R standard. In this video, we showed how you can simplify the execution of several 5G new radio tests for user equipment and base stations. The Signal View VSA software with 5G&R analysis option provides comprehensive analysis capabilities in the frequency, time, and modulation domains for signals based on the 3GPP 5G&R specification. For more information on Tektronix's 5G test solutions or to receive an in-person demonstration, please contact us today or visit tek.com.